I'm going to be giving you kind of 5 different ways that the atmosphere drives ice shelf breakup. So I'm quite pleased that last week's seminar was kind of on a similar theme, but from a more glaciological perspective. So hopefully I can give you some background and interesting results about how the atmosphere drives melt and hydrofracturing-induced collapses on ice shelves. So this is about ice shelves, so the floating platforms of ice around the edges of ice sheets. And of course, we care about ice shelves for various reasons. But here on the right, you can see some satellite images. And in 2002, scientists were pretty kind of astonished to see the Larsen B ice shelf collapse in pretty record time. So just over a month, you can see the transition from the end of January to the beginning of March in these 4 satellite images. And you can see that the ice shelf splintered into, I guess, what I would call smithereens over a fairly short amount of time. And this was not the first time that this had happened. So in the 1980s and 1960s, we had the Prince Gustav collapsing. Then the 90s, we had Larsen A. Then, of course, in the early 2000s, Larsen B. And later on, we also saw large chunks of the Wilkins ice shelf disappearing. And this is primarily due to a process called hydrofracturing, which is driven by melting at the surface of the ice shelf. So hydrofracturing is essentially the breaking by water, and to understand that process, you sort of need to have a grasp of the structure of an ice shelf. So that's what this schematic on the left here shows. It shows you a cross section through the depth of an ice shelf from this nice top layer of fresh snow all the way down to kind of solid ice right at the base. And in the middle, we've got a transitional product called Fern, and it's somewhere between snow and ice. It's got lots of air pockets in it. And that's really important because any meltwater that is generated at the surface of the ice shelf can trickle down into that Fern layer and refreeze. So the Fern layer acts as a kind of buffer, it acts as a sponge, it absorbs meltwater, and then the following winter it refreezes. And as long as the Fern is replenished with new snow at the same rate that we see melting, then that kind of structure is maintained. However, if you get more melting than snow falling and replenishing of that Fern, then the Fern layer starts to become saturated, it becomes denser and denser, and you get essentially a solid block of ice. And if that happens, we get melt collecting on the surface in melt ponds. It starts to run into existing cracks and crevasses. It starts to fill those up. Eventually, when we get to a specific threshold, the weight of that water is so great that it causes those cracks to propagate right to the base of the ice shelf, cracks into smithereens. And if that's happening all over the ice shelf all at the same time, then we see those kind of catastrophic collapse events. Now, this is a primarily atmospheric and surface-driven process. So to understand the sort of atmospheric drivers of that, I've used the surface energy balance. And this is essentially the total balance of energy that's received at the surface of the ice shelf. And it's quite a simple equation composed of the surface shortwave radiation component, so the solar radiation, long wave components, so terrestrial, the turbulent heat fluxes of sensible and latent heat, and then we've got this very small term ground heat flux, usually 1 or 2 watts per square meter. If we add all of that together, we get this term E tote, which is essentially the sum. And then if the temperature is warm enough, i.e. we're at the melt point at the surface, then we can get melting. And because melt is what we're interested in the context of hydrofracturing for ice shelves, that's what we're going to focus on here. So the reason we care ultimately about this is because these hydrofracturing-driven ice shelf collapses is primarily driven by surface processes, but it can also indirectly contribute to sea level rise because the glaciers that are restrained suddenly speed up when they're lost. So when you remove an ice shelf, like we saw with Larsen B, it's like pulling the cork out of a bottle. So the glaciers that were previously tributary glaciers into the ice shelf are able to flow unrestricted into the ocean. And that, of course, indirectly contributes to sea level rise. So this talk is going to come in two parts, and I'll warn you initially that the first part is quite a bit longer than the second, and is aiming to kind of address two outstanding questions about surface melting on ice shelves. So the first part is what causes that surface melting, and for this I'm going to be zooming in on the Larsen C ice shelf. And then also the second part is going to be looking more at what this might mean for the future. So this is an even less certain kind of question that we need to think about, as particularly as we move into a warmer and warmer future climate. So I'll dive in with the first part then, and this work is, as I mentioned, focusing on Larsen C, and the main question is trying to unpick what the main causes of surface melting are on that ice shelf. And the reason we're focusing on this one, it's the largest remaining ice shelf on the Antarctic Peninsula. The kind of southward progression of successive ice shelf collapses would suggest that it might be, if not next, then at least close in the next running order of ice shelves that are vulnerable. This work also, I should note, is part of a couple of papers that one of them's been accepted, part B is in review at the moment, so look out for those when they come out. This is primarily focusing on atmospheric processes, so very briefly I'll just go through some of the methods. So I'm using an atmospheric model. It's the UK Met Office Global Numerical Weather Prediction Model, except, of course, instead of looking at the UK, I'm looking at Antarctica, and instead of predicting the future, I am using it as a hindcast, so from 1998 to 2017. It's essentially dynamically downscaling era interim reanalysis. So we're zooming in on the Larsen C ice shelf, and we've got the domain that looks a bit like this at 4-kilometer resolution. So this is a high resolution regional climate model version. And we're using it to kind of put a magnifying glass on the area of interest. And the kind of usefulness of this model is that it's quite capable. It's non-hydrostatic, so it's very capable of getting resolving the atmospheric features that other models have struggled to represent. So regional climate models have generally been used quite a lot on Larsen C because we have fairly few observations of what's going on. I mean, most of the automatic weather station data spans at most about 12 years. So we don't have a really long record. So that means that we've, as a community, used quite a lot of regional climate models. And these three panels show just three of them. So on the left here, we have a satellite derived composite of the annual mean melt duration on Larsen C from 1999 to 2017. And it shows that we have this north-south gradient in melt duration, with more melting happening in the warmer, sunnier parts of the ice shelf. But we've also got superimposed on top of that this kind of east-west gradient. And this is related to Fern winds. Now, if we look over on the right-hand side, we can see that all three of these different regional climate models capture quite well this north-south gradient in melting, but they struggle a little bit when it comes to this east-west gradient. And we need to be sure that the hindcast, my hindcast, is capturing those processes and able to represent the processes that cause that east-west gradient in melting, because we need to, that's a very strong feature of what's happening on Larsen C. So we need to be confident that it's able to represent that. So this is my attempt to convince you that it does. Again, we've got this satellite derived kind of composite and on the left, and then on the right, we've got 20 years worth of cumulative melt amount simulated by the Met-UM hindcast. So we're trying to reproduce this north-south and east-west gradient, and I would say that it does. We can see this kind of characteristic C shape, which is particularly pronounced in certain years. So, for example, 2006-7, 15-16, 16-17, etc. We also see the same kind of high melt years in observations and the hindcast, and it captures that interannual variability quite well. So I'm quite confident that the MET-UM can represent those conditions pretty well. And this is one of the first, not the first, but one of the first models to be able to do this in a pretty comprehensive way. So to figure out what the main causes of melting are on this ice shelf, I'm using what I've called regimes, and I'm trying to explore certain kind of conditions which I've identified from the literature, but also from things that we know are important on the ice shelf. And this is things like the southern annular mode, which is the dominant mode of variability in the southern hemisphere, related to the strength and positioning of the circumpolar westerly winds. Of El Nino, the Larsen C low, which is a climatological low pressure center, and then a whole bunch of other kind of more localized features such as barrier winds, Fern events, cloudy conditions, sunny conditions, all of these sorts of things. So to detect when these kind of dominant conditions are occurring, I've used a set, what I've called indicator variables, which tell you something about whether or not those are occurring. So for example, if I'm interested in sunny conditions over the Larsen C ice shelf, I've taken the solar radiation fluxes within the box that LCIS, the Larsen C box, and if it reaches a certain threshold, then I can say that sunny conditions are occurring. And I've done something similar for each of those different sets of conditions. One word of warning, though, is that these regimes are not independent. So you can get sunny conditions happening at the same time as Fern conditions. You can have Fern conditions happening at the same time as positive SAM conditions. And many of them are related and interplay with each other, which will become apparent later. So the main question, I know it's on everybody's lips, is which regime is going to top the charts? Which are the most important? Because no one has really quantified which the most important are for driving that surface melting over the ice shelf. And it's many papers have drawn out the kind of some of the most important ones, but very few have actually either ranked them or made an attempt to quantify them. So this is my attempt at doing that. And I'm not sure how many of how my UK focused top of the pops joke is going to go down, but with a US audience, but I will do my very best to give you a top of the pops rundown. So in at number one, we have got the first order driver of surface melting, and this is shortwave radiation. Probably won't come as a surprise to any of you. So if you'll recall, that north-south gradient in melting is related to the amount of shortwave radiation we get. And solar radiation dominates the surface energy balance throughout the year. We get 24-hour sunlight in summer, and that's why we get 90% of melting happening during the summer. The highest correlation between melt flux and any other variable is with net shortwave radiation. And the shortwave radiation is related to the amount of cloud. So you can see already how the sunny conditions and cloudy conditions might be related to each other, because cloud really strongly controls how much long wave and shortwave radiation is received at the surface. So on the right here, we've got the first of many composite figures. So this is an average composite of conditions when the sunny conditions are diagnosed. And this is all for summer for now. On the left-hand panel, we've got synoptic meteorology. So the contours are mean sea level pressure. We've got vectors for 10-meter winds, scale vector at the top. And then the colors show you the mean daily maximum air temperature anomaly. Then on the right, we've got melt flux anomalies, and all of this is relative to the climatology derived from the model. So what we can see is that during sunny summertime conditions, we have very calm still winds primarily. The temperature, the maximum temperature anomalies are virtually zero, and that's because you often get sunny conditions in the summer, so the climatology is mostly sunny, and you get really considerable and extensive melt flux anomalies. So we're not just seeing melt confined to specific locations on the ice shelf, we're seeing it all across the ice shelf, and the magnitude of those anomalies are quite large. Now, number two is, again, perhaps unsurprisingly related to Fern winds. So we see that east-west gradient in surface melting is related to Fern winds. And Fern are these kind of warm, dry winds that are formed when air gets forced to flow over very steep terrain like we have on the Antarctic Peninsula. And they cause temperatures and wind speeds to increase and humidity to decrease on the lee side of mountains. So these are associated with very large sensible heat fluxes, negative latent heat fluxes, and they're known to be really important, and they drive this kind of north-south, this east-west gradient and concentration of melting in the northwestern inlets of Larsen C. Now, what we found is that they're really important, or especially important, in non-summer seasons, when shortwave radiation is less of a factor to drive melting. And this figure that you're seeing here shows you the percentage of time that Fern are occurring over Larsen C, and this is kind of zoomed in to only look at the actual ice shelf. The contour here is 50-meter elevation, so you can see that there's concentration in these inlets. So Fern are occurring much more strongly in the immediate lee of very steep terrain, like we have the peak here. And this is kind of consistent with what we would expect from the theory, and also consistent with what we see in the satellite observations. So that's really good. Another thing is that we see most common Fern occurrence in the spring, but the largest impact on melt is in autumn, so March, April, May. And just as a point of interest, Fern are 27% more likely to occur in the inlets, so over here, versus ice shelf stations over here. So we're going to look at some composites. So here we're looking at March, April, May, which is, of course, autumn, and this is again some composited conditions. We can see very strong cross-peninsular flow, which is what we know causes those Fern winds, and it drives these very positive temperature anomalies. So we see this characteristic, very C-shaped set of melt anomalies where we have lots of melting concentrated in inlets. So the effect of Fern is quite strong in these inlets, and particularly in this season, but also in September, October, November. And those two shoulder seasons explain about 4 and 5% of melt. Now, number three is cloud. And I mentioned earlier that cloud exerts a strong control on the surface energy balance via its effect on radiative fluxes. So cloud has the effect of reflecting incoming shortwave radiation and absorbing and re-emitting outgoing long-wave radiation. So it can change the kind of balance of fluxes. And here we've got a table that shows correlation coefficients between melt flux and various different parameters. Now, some of them are pretty low, so take with a pinch of salt. There's a lot of processes going on. But generally, we see that when we have more cloud in the summertime, you get less shortwave reaching the surface. So, for example, cloud fraction, indicated here, CF, is negatively correlated with melting in the summer, unsurprising perhaps. But in the winter, when we have no solar radiation, it actually results in, it's a positive correlation because it results in more melting. The cloud phase is also very important, particularly the liquid phase, and that's ice water path and liquid water path here, IOWP and LWP. We also find that cloud can initiate or sustain melt, and this is consistent with previous work as well. So in summertime, you get cloud preventing shortwave radiation reaching the surface. And if we focus here on this summertime set of composites, you can see that. So it reduces temperatures or maximum temperatures and reduces the amount of melt that goes on over the ice shelf. So this is anomalies again. Whereas in the shoulder seasons of spring and autumn, you see the opposite. So the cloud warms the surface and can initiate melting in the right conditions, but the right conditions is the kind of operative word there, because it's not necessarily enough to trigger melting unless it's warm enough. Now, because cloud generates positive total fluxes, so E tote in that equation for the surface energy balance, the energy is available to do that melting work. It just depends on the temperature. So if the temperature is at the melting point of 0, then cloud can drive melting. Now on Larsen C in kind of spring or autumn, temperatures sort of hover around about 0 but below. So in March, April, May, the average temperature is -1.1 degrees C. So if projected temperature trends kind of continue, then it could be the case that we're likely to see more cloud-mediated melting in those shoulder seasons. And I've called that the kind of Greenlandification of Larsen C, because we've seen that quite a lot in Greenland, where very thin but extensive low-level liquid clouds can trigger melting events of several days at a time. And this is what happened in 2012. Now, number 4, the last one, is large-scale circulation. And this is sort of a cheat, because large-scale circulation impacts all the other factors as well. But here I'm going to focus on 3 of the kind of regional large-scale circulation patterns. So I mentioned them at the beginning, but we've got the southern annular mode, which is related to that belt of westerly winds. We've got ENSO, which is of course related to tropical Pacific sea surface temperatures. And then we've got the Amundsen Sea Low, which is that climatological low pressure center off the west coast of the Antarctic, and where it is and how deep it is can impact the flow over the Antarctic Peninsula. So here again, we've got some more composites, and again, we're looking at the summertime this time. We've got positive SAM, so winds closer to the continent, negative SAM further away from the continent, La Nina and El Nino conditions, and then deep Amundsen Sea Low conditions. Overall, the deep Amundsen Sea Low, positive SAM and El Nino conditions increase melting, and negative SAM and La Nina decrease melting, relative to the climatology, that is. But what might be interesting is to look in different seasons. So here we see just positive SAM conditions, and this is for autumn, so March, April, May. In positive SAM periods, we get very strong cross-peninsular flow, positive maximum air temperature anomalies, and you can see that that's translates into this positive melt anomalies almost in that characteristic C shape that is a clear signature of Fern. So we can infer from that pattern of melt anomalies that Fern and SAM might be linked, something we also know from theoretical considerations and previous work. Or we can actually go one step better and we can directly look at the relationships between them. So here we've got some correlations between observed SAM index and modelled Fern occurrence. So the table shows you some Pearson correlation coefficients between those 2 variables, and the chart is a more visual way of thinking about that. And we know it makes sense that we have these strong positive relationships, because those large-scale circulation patterns really influence the synoptic and local scale meteorology. So positive SAM conditions are associated with those strong cross-peninsular winds, and we know that strong cross-peninsular winds result in Fern winds. So you can see how the kind of large scale impacts the localized scale, and therefore melting on the Larsen C ice shelf. So a little summary of some of the most important things that drive melting and suppress melting on Larsen C. I didn't go into too much depth about the ones that suppress it in the interest of time, but I'll just give you a brief rundown. So the most important regime or set of conditions for suppressing melt is barrier winds, where we get these very cold katabatic outflow from the continent. Then we've got negative SAM conditions, followed by cloudy conditions, and this, I should also say, is all for summertime. And then finally, we've got La Nina conditions. And then those that enhance melting are a deep Amundsen sea low, sunny conditions, Fern conditions, and then positive SAM conditions. And remember, all of these overlap and co-occur, so you can see how these are all kind of influencing each other. So for example, the Amundsen sea low sets up conditions for Fern to occur, also sunny conditions to occur. So it's almost like a Fern plus sunny equals ASL. So the chart rundown, hopefully we've won top of the pops. In at number 1, you've got shortwave radiation. Fern winds are especially important in non-summer seasons, and they're number 2. Then we've got cloud, which strongly mediate the surface fluxes and may become more important in future. And then finally, we've got large-scale circulation, which sort of establishes conditions for any of those localized drivers to drive melt. I just wanted to say also, the data is available and it's on the CEDAR archive. And if anyone is interested in using it, I would really encourage you to do so. It's a really big data set if anyone is interested in the central Antarctic Peninsula, and there's a huge amount of stuff that I wanted to do but couldn't do. So if you're at all interested in using it, you can find it here, or get in touch and I can point you in the right direction. So I think this is a really good point to dive into part 2, but does anyone have any questions before I do that?
Silence.
Silence, pin dropping.
Give it a minute, someone might be struggling to unmute.
Well, we can always save them for the end as well.
Christopher has his thumbs up.
I had one question. Can you hear me?
Yes.
What resolution do you think that models typically need in order to represent the phone winds adequately? You're using 4 kilometers.
Yeah.
What do you think the minimum you would need to adequately represent that effect would be?
That's a good question. I think some of it is related to resolution, some of it is related to models that are hydrostatic versus non-hydrostatic. So the MAR model and the RACMO model have both been used, and they are hydrostatic, which means that they can't really go below 5.5 kilometers, which doesn't seem to be quite sufficient. I did quite a lot of work with kind of case studies looking at specific Fern events, and we tried at 0.5, 1.5 and 4 kilometer resolution, and there wasn't really a great deal of difference between 1.5 and 4, which is why we went with 4 for this particular hindcast, because the benefit, the marginal benefit you got from decreasing was not really outweighed by the computational cost. So I'd say that 4 or 5 kilometer resolution is probably enough, but it also might depend on the specific model physics as well.
Great, thanks.
Awesome. I might continue with part 2, and then if anyone has any questions, you can save them up to the end. I'm happy to take them then. Okay, so this bit is going to kind of switch tack a little bit and zoom out to look at the kind of Antarctic as a whole, and look more at the future and think about what is likely to happen to ice shelves with ongoing future warming. And this primarily is part of a paper that we published earlier last year in GRL, and my colleague Chris Kittle also wrote a really excellent paper that was in the cryosphere. So if you are interested in this, I'm just pointing you towards those as well. So here we're using another regional climate model. This time it's at much lower resolution. It's at 35 kilometers. And it's forced with 4 different CMIP class GCM simulations of the future out to 2100. So they're selected for their ability to represent modern Antarctic climate. And if you're interested in that, that Kittle et al. Paper is a good place to start with the reasons they were selected and things like that. So here, instead of thinking about the surface energy balance, we're thinking about the surface mass balance, which is, of course, the balance between inputs, snowfall and rainfall, primarily snowfall, minus sublimation, evaporation, melt, and runoff. So the overall surface mass balance is primarily dictated by the balance between snow and meltfall, and that's the main driver of that balance. But if you'll recall from that kind of like satellite imagery at the beginning, the presence of liquid water at the surface of an ice shelf suggests that the ice shelf has become kind of densified and saturated with meltwater, such that there is nowhere for that meltwater to go. So when it starts collecting and ponding on the surface, it implies that we've got an ice shelf that's saturated with meltwater and therefore vulnerable to collapse by this hydrofracturing mechanism. So we took this kind of runoff term, which essentially in MAR means liquid water at the surface. And we looked at the amount of runoff that's occurring at 1.5, 2 degrees and 4 degrees of warming. And we looked at increments of warming rather than kind of time periods to get a kind of consistent idea of what might happen in a more kind of intuitively relevant space. So this is some of the first results, and these are maps that show you melt, runoff, and the total surface mass balance difference from the kind of the historical period from 1980 to 2009 at 1.5 degrees Celsius. So the blue colors for melt and runoff are negative or decreases, and the reds are an increase for melt and runoff, and then the opposite is true for surface mass balance. So the blues are kind of gaining mass and the reds are losing mass, or differences rather. So this is 1.5 degrees, and we can see that the majority of the color is concentrated on the Antarctic Peninsula. We see some increases in surface mass balance over high ground, off ice shelves, so on the actual ice sheet itself. And then on ice shelves, we see increased melt and runoff and decreases in the surface mass balance. If we look at the 2 degrees, we see the same sort of picture. It's just increased slightly from that 1.5 degree picture. And then if we skip ahead to 4 degrees, that picture is very much more intensified. So we see lots more melt and runoff occurring at higher temperatures, but you also see quite a lot more snowfall happening over that steep peripheral terrain around the edge of the ice shelf, ice sheet even, and that surface mass balance over ice shelves, which is of course what we're interested in, is decreasing relative to the historical period. Now, another way of showing that melt and runoff amounts increase is by looking at it kind of summed across all ice shelves. So that's what you're looking at here. So again, we've got melt, runoff, and surface mass balance. The kind of the different scenarios, different colors are color coded, and then the different models are shown with different markers. The circles are the multi-model mean, and that's, I guess, what you I would draw your attention to. And we can see that as we have more greatly increased levels of warming, melt increases, runoff increases, and surface mass balance declines, as we saw in the previous plots. But we also see that there's this kind of non-linear effect of warming on melt and runoff, and this is related to the melt albedo effect. So we get more warming, more melting, darker surface, more warming, more melting, etc. We also see that there's quite a lot larger spread of results at 4 degrees, and that's kind of consistent with work that shows you have more scenario uncertainty around about mid-century, and of course the longer you go out into the future, the more uncertain things become. So that's just a reflection of that. You also see pretty consistently the same models having either the highest or lowest melt and runoff and surface mass balance respectively. So for example, NOR ESM consistently shows the least surface mass balance changes. Now, because we are interested in kind of where ice shelves or which ice shelves are going to become vulnerable to destabilization by this hydrofracturing mechanism, we're looking at the spatial area. So here, all of these plots are time series of what I've called ice shelf runoff extent, but this is essentially the spatial area where runoff is occurring over ice shelves over time. And you can see in this first panel that I've indicated the rough 30-year periods where each level of warming is simulated, and that's the multi-model mean ones. And what we can see is this kind of this is broken down into regions, I should also note as well. So this headline statistic, so 1/3 of ice shelf area could become vulnerable to collapse at 4 degrees, is based on this this panel, but it masks some of the regional variations. And you can see that in the other 3 panels. So for example, in the Antarctic Peninsula, you have a fairly steady increase through time as temperatures warm in the amount of ice shelf area that's undergoing runoff, but it increases from around about 40% in 1980. So this suggests that there are other processes that are going on, because not all of these ice shelves have collapsed, and that's to do with the fact that some ice shelves are quite resilient to hydrofracturing. That's quite different to the East Antarctic, where we see a rapidly increasing contribution over time. The gradient is pretty steep there. And then it's very different again to what's happening in the West Antarctic. And in the West Antarctic, there's a fairly limited area undergoing runoff, and therefore a limited contribution to destabilization until about 4 degrees, and that happens around 2070. And that's mostly because in the West Antarctic, we see a huge amount of snowfall that balances that melting, so it doesn't have such considerable effects. Now, the limitation of this kind of analysis is that it tells us about the total spatial extent, not whether melt and runoff is concentrated on certain ice shelves, whether it's evenly distributed, whether we're seeing all the melting and runoff happening on one ice shelf in the region, or whether it's little bits of every ice shelf in the region. So to kind of think about that, we have to go back to a more map-based approach. So that's what we're doing here. And here we're looking at the runoff duration, so the number of days per year when runoff is simulated on ice shelves. And this time we're looking at individual models. On the left, we've got 1.5 degrees. On the right, we've got 2 degrees. You can see there's fairly limited differences. Again, we're seeing the highest runoff duration on the peninsula, but also some parts over here. I think that's the Amory, and then the West Ice Shelves, Shackleton. If we skip ahead to look at 4 degrees, you can see some of the intermodal variability, but here, if I draw your attention to the multi-model mean at 4 degrees, you can see this kind of overall picture. And runoff is, of course, much more common on the Antarctic Peninsula. It's much more common at 4 degrees than the other increments of warming. And you can see that there's ice shelves in pretty much every region of Antarctica that is undergoing fairly considerable runoff of upwards of a month per year. Now, some of those ice shelves are resistant to hydrofracture already, so particularly some up here in the East Antarctic are pretty resilient. For example, the George VI is kind of stuck on every side by rock, so it's quite resilient to fracture, and others are less so. So figuring out which those are is really important. And to do that, we kind of cross-referenced our results with those of Lyell. And this is a really interesting paper that looks at the vulnerability of ice shelves to hydrofracture from a more kind of glaciological perspective. And we essentially identified those ice shelves where we found considerable runoff and where Lyell found the ice shelf could be vulnerable to collapse. So those ones are the Larsen C ice shelf, which is perhaps unsurprising given the first half of this talk. Then we've got the Wilkins, the Pine Island Glacier ice shelf, and then the Shackleton. So although there are some ice shelves that are resilient, we've identified several that are vulnerable to hydrofracturing based on cross-referencing our results of, where the most runoff is simulated, and those of Lyell. And we found that these 4 ice shelves, the Pine Island, Wilkins, Larsen C, and Shackleton ice shelves, are the most vulnerable to hydrofracturing. Some of them are, as I said, structurally resilient to these kinds of collapses. And overall, if we limit warming to 2 degrees, the area of ice shelves that are vulnerable to hydrofracturing-induced collapse is halved relative to 4 degrees. So if you're interested in that, I've done a bazillion science communication attempts. There's a video up on my YouTube channel, which is Dr. Gilbert with a Z. And then I wrote a couple of kind of specialist mainstream articles if you're interested. So to kind of sum up the whole talk, atmospheric processes are driving melt over ice shelves on the continent, and that's really important as a driver of melting across ice shelves. And climate change has the potential to alter which of these is important. It might change the factors that are driving melt in the future, whether that's increasing temperatures and meaning that cloud-mediated melt becomes more important, or increasing the amount of runoff that occurs. Especially on the peninsula, that's likely to happen sooner rather than later. We might see trends towards more kind of Greenlandic conditions on the Antarctic Peninsula and potentially West Antarctica. And there's also this idea that a more positive SAM trend might start to emerge again, which, as we've seen from the relationship between SAM and Fern Winds, could start to drive more melting in places like Larsen C, but also elsewhere on the peninsula. So this is consistent with some other recent studies, like we've seen here. And ultimately, I'd say that Antarctica is likely to contribute more to sea level this century than we've seen so far. Mitigation is, of course, required if we want to avoid the worst case scenarios. And if I did have to place bets, I would say that maybe I'm biased, but it would seem like Larsen C could be one of the next ice shelves to see considerable melting. So it's underlining yet again the need for strong and stringent mitigation to prevent that worst case 4 degree scenario happening and make it much closer to 1.5 or 2. So thank you very much. If anyone has saved up any questions, now is probably a good time. Thank you very much.
Thanks, Ella. Do we have any questions from the group? I see Letty is clapping. Christopher says, great talk.
I have a question.
Lovely.
So explain again, maybe, the difference in the quantified melt and runoff categories.
Hang on, let me find my slide. Here, you mean?
Yeah.
So in MAR, runoff essentially means, so melting is the meltwater that's produced, and runoff is the water that collects at the surface that is not balanced by refreezing, and it doesn't contain a liquid surface water routing scheme, which means that any kind of runoff that is produced is immediately exported to the ocean. So it's used as a kind of crude indicator of liquid water ponding and collecting at the surface. Does that make sense?
So is that suggesting that melt is really a 1D thing, that if you just, the excess of melt over runoff would really just be meltwater falling into the Fern and refreezing?
Yeah, exactly, yeah.
Okay, thanks.
Thanks, Laurie. We have Rod has his hand up.
Hey, thanks for the presentation. Do I understand it correctly that in fact melt is the only process causing the hydrofracturing, and that it is a kind of independent of changes in accumulation rate, for instance? Because that has been suggested also to play a role, and I don't see that back here. So I presume that in this analysis, you only take the change in the ablation or melt and runoff as the driving process. Is that correct?
Yeah, in both of these, actually, yes, we're assuming that the kind of the surface melt driven component of it is, well, I mean, it's the focus of this particular work. That's not to say that there aren't other factors that either mediate or accelerate melting and hydrofracturing even. So, for example, more accumulation would reduce the amount of hydrofracturing vulnerability. But here the focus is surface melting, because that's the dominant component. Yeah.
And how do you judge the importance of interannual variability in these processes? Because, well, I think it's fair probably to say that the regional climate models are maybe not too good in reproducing the interannual variability in comparison with observational data. And it may well be that you have a couple of years with enhanced melt, which would then lead to hydrofracturing.
Yeah,
do you
exactly.
judge that to be important?
Yeah, we actually, in the first part of that Larsen C paper, we did look at specific case studies. So there's a few years where there was really strong Fern-driven melting, for example, and you see extremely high melt rates. And my gut instinct is that those sort of intense events do actually drive a large component of the melting that would contribute to hydrofracturing. So, for example, in the Larsen B case, it's been kind of documented that that specifically intensive melting and warming periods immediately preceded that collapse. So it was almost like an intense Fern-driven, synoptically driven event that caused that, was the trigger essentially. So you had years and years of preconditioning, but then the immediate trigger of its collapse was intense melting driven by the atmosphere. Does that make sense?
Yeah, I think so. Yeah, particularly for Larsen B, I think it makes sense. For Larsen A, I think this is much more complicated. This is not so clear, I think.
Yes, yeah, I think Larsen C has, obviously it's larger. So again, it makes it potentially more complicated. And we see those sorts of events like we saw with Larsen B. Like you say, Larsen A is slightly more complicated. So it would make sense that those sorts of events, from my work, it's definitely been clear that specific intense events drive a large component of melting, and that's also been shown by someone called Andy Elvidge at UEA. So I think a large chunk of the melting happens in intense bursts.
Yeah. Okay, thank you very much.
We have a couple of questions in the chat. First one is from Christopher Schumann. He says that his microphone is faulty on his computer, so I'm just going to read it out. I hope that's okay. So he's wondering if you've compared model melt to passive microwave melt record for any of the larger ice shelf areas.
I'll assume that's for the second part, I haven't actually. However, there's been quite a lot of validation done of MAR anyway, by my colleague Chris. So the work we did for that GRL paper, which was this second half of the talk, was essentially assuming that the validation is it's done already. For the Larsen C stuff, I haven't actually ever compared it directly. We did some validation work looking at the sort of overall characteristics in comparison with ASCAT satellite data, but the majority of the validation was done against weather station observations.
Next up, we have Vivian in the chat. Vivian, would you like to unmute by any chance?
Yes. Yeah, I had a question. I mean, we're showing a pattern of a greater warming and melting at the part of the ice shelf that was in contact with the actual inlet, the grounded areas.
Yeah.
And so I'm just wondering about the implications of that for hydrofracturing and also whether Larsen B showed the same pattern when it began to hydrofracture and then eventually collapse.
Yes, is the short answer. So again, I did another case study looking at the collapse of Larsen B, and that's in that first part of this paper as well. And like on Larsen C, you see the concentration of fern occurrence in the immediately of that steep terrain. And I don't actually know if that implies, or if it actually was observed that hydrofracturing began closer to the grounding line, but it could be indicative of that. There would certainly be much higher melt rates closest to the mountains. And of course, if you start melting and initiating that kind of process closest to the mountains and furthest away from the calving front, then you're more likely to get the entire ice shelf disintegrating, I would suppose. But you certainly do see the same patterns of surface melting and fern occurrence, broadly speaking, over Larsen C and Larsen B.
Thank you.
We have another question in the chat from Christopher. Thanks. Fortunately, there is still time to track the two types of melt data for the bigger shelves. Steep terrain and also ice edge changes will be challenges, of course.
Indeed.
Could I ask one more question?
Yeah, please.
So following up on your response to Vivian, do you have any reason to believe that hydrofracture in the inlets would push out the ice for an entire ice shelf, or is it going to be held in place by all the ice shelf outboard of that, so that you potentially fracture it and then it freezes up again?
Yeah, I don't actually have a solid set of reasoning for that. I've read somewhere that it can initiate closest to the grounding line if you get more melting there, but honestly, I don't actually know the answer to that.
So prior to Larsen B blowing out, it did have melt all over the place, right? It wasn't just fern induced melt right at the grounding line.
Yeah, in Larsen B there was many years of fern melting, but you know that's commonplace on the Antarctic Peninsula because it's such a dominant wind direction. And there was a very, very anomalously warm summer, and then you had that kind of immediate trigger of fern winds. But yeah, you saw melting across the whole Larsen B ice shelf, but potentially more concentrated in those inlets. But certainly there would have been surface melting across the entirety of Larsen B. Yeah.
I see Rod still has his hand. Did you want to ask another question, Rod?
No, sorry.
Do we have any perhaps final questions from the group? We're coming up here on noon in New York.
Nearly lunchtime.
Yeah, I'm ready for my lunch.
It's 12 o'clock.
Oh, I'm
There
not
we
sure what that
go.
was.
12 o'clock.
Okay. Well, thanks everyone so much for joining us, and yeah, getting lots of claps and great presentations. And yeah, thanks again, Ella, and hopefully we'll get you back. If you ever have anything new you'd like to share, please let us know.
Yeah.
And yeah, I hope everyone has a great rest of the day.
Cheers. Thanks for having me.
Thanks, guys.